Okay, we're ready to start the notes for 4A for the Math 4 class. And yeah, we're already getting this. It's too early for December, although I do not share that sentiment, but I get a lot of that right about now. I was playing Christmas music to whatever I was grading this past weekend. Now, we're going to revisit the idea of sine, cosine, and tangent. And we're also going to pick up on the ideas of secant, or rather cotangent, secant, and cosecant, and the fact that they are reciprocals of sine, cosine, tangent. And we'll get to that eventually. But first, I wanted to stop and talk about Pythagorean triples. Understand that what we call a Pythagorean triple is where these whole numbers all fit into the idea of a squared plus b squared equals c squared. And they fit it perfectly. 3 squared plus 4 squared equals 5 squared, like a dream. All of these work in that fashion. Now, when you stop and think about it, not every triangle is going to work out that way. Pythagoras ran into this problem with the most basic of triangles when he said, all right, there's a 1 here and a 1 there. 1 squared plus 1 squared equals 2 squared. 1 squared was 1 squared equals 2. Which means that I'm going to have the square root of 2 on that side, and that's what drove him nuts, because he had no idea where to find square root of 2 on the number line. Where is that going to show up on your ruler? It's not. And, they had no concept of decimals back in those days. And so it was evil to him. But when he came across these sets of numbers and they fit in just perfectly, he felt like there was like some sort of cosmic significance, like the gods were smiling on him every time that he used these numbers to create triangles. And and I will say something, that this guy right here does not follow the pattern of the other 3 or 4. You'll notice that the other ones go, the first number is 3, then 5, then 7, then 9, and you could actually keep going. Then the middle number is 4, then 12, then 24, then 40. And those middle numbers are increasing by, plus 8, plus 12, plus 16. The next one would be plus 20. And of course, the last number is always 1 more than whatever the guy was in the middle. And so there are patterns that you can follow to create some Pythagorean triples of very large size. But I will say that the stuff that you will encounter usually is in these last 2 groups. I would say probably 75% of what you'll see is in the 3, 4, 5 group. And then 5, 12, 13 accounts for like another 10%. And then it's kind of scattered with the rest of these. But here's something you need to understand, is that when you were in middle school and you worked out a problem and you got to the answer, and the answer was 6, and you said, ooh, a nice round number, I think I did it right. And yeah, the people who created the problems were doing that intentionally. That, when you got a nice round number instead of some ugly decimal, you were more likely to feel confident about your answer and feel like, oh, I must have done this right. And that has not changed in high school. There are a lot of cases where they'll give you a right triangle and they'll say 3 here and 5 there, and you need to find x. And so you're going to say 3 squared plus x squared equals 5 squared. And so eventually you would solve and find out that x was 4. Well, if you already are aware of these Pythagorean triples, then the next time that they give you a problem that goes something like this, there's a 13, there's a 5, and you need to solve for x, then you can look at it and say, oh, that's a 5, 12, 13. And this is now becomes a matter of recognition. You know how to do it. You know how to do the 5 squared plus x squared equals 13 squared. You can go through the method, but just because you know how to do it doesn't mean that I'm going to expect you to do it every time. If you recognize the triples, then you can skip right past it and say, oh, x must be 12. Now, let me show you another little trick about this. And I do this because you will be encountering these triangles from here on out. And you can take 3, 4, 5, and you can multiply these by the same number. Let's say that we double each one of those. 6 squared plus 8 squared equals 10 squared. It still works. I can multiply these triples by any number I want to. 50 and 120 and 130. I multiplied everybody by 10. I can multiply everybody by 0.1 and move the decimal over one place, and it still works. Now, those aren't exactly whole numbers, but still, I would consider them a part of that family because they are basically one multiple away from being 3, 4, 5, or 7, 24, 25, that sort of thing. So now, here's the fun part. If you can catch this, this will help you greatly. Let's say that I had 9 here and 15 here, and I suspected that this might be one of these families. Well, my first question is, what is the common factor here? Well, 15 and 9, common factor is 3. Well, 15 divided by 3, 9 divided by 3. Hey, wait a minute, this is a 3, 4, 5 triangle. But my factor here was 3, so that must mean that x is 12. If my common factor times 3, 4, 5 gave me 9, 12, 15, that's multiplying by 3. And so you can play that game with it. Yeah, tell you what, I'll give you a chance to mentally practice with this. Let's say that I have a right triangle like this, and I have 15 here, and I have 36 here. And I want to know what x is. So I'm going to give you a moment to figure out what is the common factor. And so which family does this belong to? If you thought that the common factor might be 3, you would be correct. And it turns out that this is actually a 5, 12, 13. Now, if my common factor was 3, 13 times 3 is 39. And bam, there I am. That took me all of 5 seconds. Yes, I could do 15 squared plus 36 squared equals x squared and do it the long way. But, and you can always fall back on that if you don't see a pattern. It will always get you to the answer. But I'm here to tell you that you're going to see more and more of these Pythagorean triples showing up in your problems. And if you can see the pattern and go ahead and know what the answer is without having to go the long way, that just saves you a little more time. You didn't have to spend time here. Now you have time extra to spend somewhere else where you really need to bang your head over it. So anyway, that is as far as I wanted to go with that. Now let's get into the sine, cosine, and tangent. Now, originally the idea was that you have similar triangles here. If these triangles are similar, and if I have the same angle going on here, and I do here, then, if this is a 3 and a 4 and a 5, and if I have the same angle here, then I'm going to wind up with a 6 and an 8 and a 10. Then one of the things that they noticed is that if these are similar triangles, and I say 3 over 4, the matching part is going to be 6 over 8, which reduces down to 3 over 4. And so they noticed that with these similar triangles, when I set up a ratio of one side over the other side, it gave me the same decimal. 3 over 4 is 0.75. 6 over 8 is 0.75. And so after a while, they started doing, if it's opposite over hypotenuse, that's what they would call the sine. If it was adjacent over hypotenuse, they would call that the cosine. And then if it was opposite over adjacent, they would call that tangent. Now understand that what's going on here is that once you have identified which angle you're going to focus on, and it's never ever the right angle, it's always one of these two guys. but it's whoever's got traffic here, either an X here or a number here or something like that. And then our first move is to figure out who's opposite of that angle, who's on the opposite side, and that gets to be the opposite leg. Opposite is always across from whatever angle we're focusing on. Hypotenuse, of course, is always across from the right angle. And so I would do those two first, and whoever's left over gets to be the adjacent. All right. Adjacent sometimes gets confused if you try and do him too early in the problem. Sometimes you'll put the adjacent over here because it is next to that angle. But then you've got nowhere to put the hypotenuse except a wrong spot. So I always do adjacent last. Now, something else I want you to notice is the idea of Sohcahtoa. You can see it lining up right here. Sohcahtoa. Sine is opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent is opposite over adjacent. And it gives you a shortcut to remember which parts belong over which ones for sine, cosine, and tangent. We're going to need that where we're going. Now, I presume that most of you have seen much of this before. We're going to throw in a new wrinkle with cotangent, secant, and cosecant. And I'm going to explain what they are in just a minute. But first of all, before I can do ratios over here, I got to know what this missing side is. This is my opposite side, and for the moment, I'm calling it little a. You'll notice that in these kind of triangles, they have a tendency that if this corner is big A, then there's a little a across from it. If this is big B, capital B at this corner, then this is going to be little b across from it. And they play that game. And so you're more or less expected to, whenever they start talking about A, B, and C, know that the capital letters are one thing and the little letters are the guys across from them. And I think I mentioned that before in class, that there's always a relationship between an angle and the side that's across from it. Now, we're going to play this game because this is not one of our Pythagorean triples. This is not 3, 4, 5 because remember, 5 would have to be the biggest side, which means 5 would have to be the hypotenuse, and he's not. So we're going to have to do this old school math going on here. Subtract the 9 from both sides, take the square root. I get square root of 7. All right, so now we're ready. Oh, and we do need to label who is. If that's my angle that I'm focusing on, then this is the opposite. If that's my right angle, then this must be the hypotenuse. And 3 gets to be the adjacent. So if sine is opposite over hypotenuse, sine over opposite over hypotenuse, that is square root of 7 over 4. Cosine is adjacent over hypotenuse, which is adjacent 3 over hypotenuse 4. And then tangent is opposite over adjacent, square root of 7 over 3. Now, I'm going to take these 3 and put them down here, cotangent, secant. And I don't know if you noticed, but there is a pattern to this: sine, cosine, tangent, cotangent, secant, cosecant. So it's like the first one is whatever it is, and then the one right after it is whatever. And that's a thing. That's a pattern. Now, here's where the fun starts. You get to think rainbow, because that's how they match up. But it's more than just matching up, because when you come to the other side of the rainbow, you are flipping your fraction. For instance, that's square root of 7 over 4 becomes 4 over square root of 7. They are inverses of each other. They are reciprocals, I think is the better term here. They are reciprocals of each other. And, we can't leave a square root on the bottom. Here's my suggestion. Move it to the top and leave a 7 on the bottom with no square root. Now, if you can simplify big 4 over big 7, then, that's a different story, but those won't simplify. Now, cosine is 3 over 4. When I flip it here for secant, I get 4 over 3. They're just being flipped over. And of course, the same thing happens with tangent and cotangent. I flip it over, I get 3 over square root of 7, which I'm going to move the square root up to the top and leave the 7 on the bottom. And of course, big 3 over big 7 doesn't simplify, so I'm stuck there. That's going to be my final answer. So there is this reciprocal relationship between sine and cosecant, between cosine and secant. It's almost as if to say sine of A is the same as 1 over cosecant of A. And we'll run into a bunch of these, basically, and we can define it the other way. I can say that secant of A is equal to 1 over cosine. They are reciprocals of each other. Okay. All right. Now, working your basic Sohcahtoa problem, especially when you have something that's not 30, 60, or 45 degree angle or something like that. If it's some oddball angle, then you are going to have to use Sohcahtoa to do this. Now, first of all, is you got to identify what angle you're focusing on. It's never the 91. Never ever make it the 90 degree angle. And of these two angles, this is the only one with any kind of business in it. So he's going to be where I focus. I'm going to focus on the 35. Now, from the perspective of the 35, this is my opposite. There's the right angle, so this is my hypotenuse. And that means that 12 gets to be the adjacent. So then I ask myself, Sohcahtoa. And so, who are the players? Who are the players in this problem? Well, I've got an x that's a part of the problem. I've got a 12 that's a part of the problem. Hypotenuse has nothing, so I'm going to ignore him. I don't need him. So my players are opposite and adjacent. Who is it that uses both of those? Opposite and adjacent. Your players here are going to dictate which one of these three that you're going to use. Because I'm using opposite and adjacent, this is going to be a tangent problem. And I know how many degrees. And Sohcahtoa tells me that the opposite goes on top, the adjacent on the bottom. That's x on top, 12 on the bottom. Now, if I want to solve for x, I'm actually getting ahead of myself here a little bit. I'm going to scroll down. Match the players with the trig ratio. That's the Sohcahtoa. And then set up the equation. Tan of 35 equals x over 12. Now you're going to solve. All right, so you're going to say, all right, I'm going to multiply by 12 on both sides. And that's going to leave me with x, which I can punch into the calculator and solve for that. One comment I want to make here is that if I had said it this way, do I know whether the 12 is supposed to be in the tan or not? Is it just tan 35? Do that, get a decimal, and then say times 12? Or did I mean for that to happen? I don't know. This is kind of like saying, if I'm going to have the square root of 3 times 2, was the 2 meant to be under the roof or not? Especially if the roof drifts over that far. Was the 2 meant to be under the roof or not? I don't know, but if I write it like that, there's no question. So that's why we write 12 tan 35, is that it's 12 times tan 35, and you can punch it into the calculator without the multiplication sign. You can say 12 tan 35, enter, and you're good. Now, this is the point where we run into people that if they're not careful, they're going to get every blessed problem wrong for the entire day because they forgot to check their mode button. Your mode button on your calculator is supposed to be degrees not radians. I'll tell you this, that most calculators, when you change batteries, the default setting goes back to radians. So every time you change batteries, you'll need to go back and put it back to degrees. Every time that you clear memory, it will reset it back to radians, and you'll need to go in and manually put it back to degrees. Otherwise, every single sine, cosine, and tangent you punch is going to be wrong. Now, let's go to the calculator and figure out what this is. And the calculator says that it is 8.40. So I might put 8.4. Now, they don't really say where to round it. And a lot of times I will tell folks that, when you're in Rome, do as the Romans do. When I look at all the other numbers in this problem, they are whole numbers. So I might just want to round it to 8. That would be rounding it to a whole number. Now, where you run into trouble is sometimes, your rounded number. And if this, I'm just making up something. What happens if this was 8? Or better yet, what happens if this was 8.5 or something like that? And I would want to say 8.4 just to make it clear that it's not the same as that. Sometimes you run into those situations where you might want to add a little extra decimal on the end of it, just so that you can show. Because remember, hypotenuse is supposed to be the longest side there is. What happens if I were solving? If I had y up here and I was solving for y, and y turned out to be 12.2, I couldn't round it down to 12 because then I'd have both sides as 12, and that's you realize how wrong that is. So maybe the 12.2, you'd want to leave that extra decimal just to differentiate between the two. So that's that happens, but most of the time you can just if they're all whole numbers, round it to a whole number and move on. All right. Now let's go on to the last example. We're going to get W, Y, and Z. Actually, Z is the low-hanging fruit right now, because these three angles add up to 180. And by the time I subtract them off, I'm going to wind up with 67 degrees. Now, some of you might be tempted to say, all right, if this is 67, I'm going to start from this one because I'm more comfortable in this direction. But I've made the statement before that if you start finding other pieces based on the work that you've done already, you might run, what happens if you got this one wrong? That means you're going to get that one wrong too. And so I am more inclined to say, no, I'm going to resist the urge to do the 67, even though it's in the right direction, and I feel more comfortable going that way. I am going to go this way, and I'm going to say, all right, 23 is the angle that I'm focusing on, because they gave me that number. There's no, possibility of me making a mistake with it. And so from that perspective, here's the opposite. There's the right angle, so here's the hypotenuse. And W gets to be the adjacent. He's the leftovers. So now I have a unique problem that I have a W and a Y that I need to solve for. I can't put them in the same problem because if you have two letters, you're not going to get anywhere. So this is going to be two separate problems. W and 18 is going to be one problem, and Y and 18 is going to be the other problem. So let's see what happens when I focus on these two first. When I look at Sohcahtoa, and I see my two players are hypotenuse and adjacent. That's adjacent and hypotenuse. This is a cosine problem. My two players told me that it was going to have to be this one in the middle. So I'm going to say cosine of 23 degrees. And Sohcahtoa tells me adjacent goes on top, hypotenuse on the bottom. So the adjacent W and the hypotenuse 18. Now I'm ready to multiply both sides by 18. And I got 18 cosine 23 equals W, which turns out to be, on my handy dandy calculator, 16.569, or about 16.6. Well, let's do as the Romans do. We'll call it 17. It rounds up. 16.569. Yeah, it'll round up 17. And it's still one shy of 18, so I'm not worried about there being any confusion about who's the longest side. And so now that we've done this, we can back up and look in the other direction and say, who are my players now for y? Y I need to solve for, and the 18 is still going to be a player. That's hypotenuse and opposite. Who uses hypotenuse and opposite? And that would be these two. This is going to be a sine problem. Sine 23. And Sohcahtoa tells me opposite on top, hypotenuse on the bottom, y on top, 18 on the bottom. So I'm going to multiply both sides by 18. And I get 18 sine 23 equals y. And that is going to be about 7. 7.033 and some change. But that gives us w, that gives us y, and that gives us z over here. I guess I need to circle my answers. W, y, z. And that should bring us to the end of the notes for 4A.